All right. So we're going to be talking about connecting the equations of rational functions to its graph. So everything we were talking about before we had our long break there was analyzing the graphs, analyzing rational functions, talking about asymptotes, zeros, holes, y-intercepts, x-intercepts. That's all kind of information that we were finding. So we're going to go through this, finding that information again, but eventually here, once we get into this lesson, we're going to focus on those horizontal asymptotes and how to actually find where they are or what kind of asymptote they are. So far we have seen connections between factors and terms in the equation and what their graphical consequences are. Let's review those for a moment. So we're going to review them, and this works good since we weren't here for a few days. So non-canceling factors that are in the denominator of a rational function, if they're non-canceling, what can you find with those? Yes, vertical asymptotes. I'm just going to abbreviate. If you want to write it out, you can. Non-canceling factors in the numerator. Marie? Zeros. Canceling factors in the numerator and denominator. Marie? Holes. And the quotient of the constant terms. The quotient of the constant terms. Tori? Yes. Y-intercept. If we look in the next column here, the next row, they give us the rational function. They've already factored it for us. So we can see that those factors would end up canceling there. So they give us that factored form. Let's go ahead and figure out this information down here that they ask us for. Identify the factor and set it equal to 0. Well, they're talking about this one up above for the vertical asymptote. So which one do we need to set equal to 0? For vertical asymptote? Which one is it? Marie? The first one where? Top or bottom? The top one will find us the zeros. Yep, we're trying to find the vertical asymptote, so it'll be the bottom. So x plus 2 equals 0, so x equal to negative 2. That's where the vertical asymptote would be. The next one is the zeros, so that's where we set the top one. Negative 2x plus 3 equals 0. Three over 2 is your answer. Identify the factor and set it equal to 0. The one for the canceling one, well, that was the x plus 1. We already showed that there. So x plus 1 equal to 0. So x is equal to negative 1. And the quotient. What is the quotient of the constant terms? Who has that? It is 3 over 2. Now I'm also going to write this in that box. We have 3 over 2, and that is the y-intercept, so the x value has to be what? X value has to be, Tori? 0. So I'm going to write the point 0, comma 3 over 2. That's your y-intercept. So if we actually go ahead and look at our graph here, we can confirm where some of this stuff is. So vertical asymptote at negative 2. Well, we can see they already have the line there. That is where the vertical asymptote is. Says we have a 0 at 3 over 2. So if we go, that's the same as 1.5. So at 1.5 we see it does cross the x-axis. It says we have a hole at negative 1. So if we go to negative 1, we see there is a hole. And the y-intercept is 0, 3 over 2, so 1.5. If we go up 1.5, we do have a y-intercept at 3 over 2. So this is a lot of the find this, and we're able to plot it on a graph to start to find how our equation, our rational function, is actually graphed on the coordinate plane if we didn't have it. All of that work we did up here, though, we noticed we did not figure out the horizontal asymptote. So that's what we're going to try to focus on today, how to find that and how we know where it's at. Before we move on, we've already talked about this a little bit, just reinforcing it at the bottom. So it says when the equation has a factor in the denominator that does not cancel out, then the graph has a vertical asymptote. Again, I'm just going to abbreviate. At the x value that makes the factor equal to 0. So vertical asymptote. When the equation has a factor in the numerator that does not cancel out, the graph has a 0. When the equation has a factor in the numerator and denominator that does cancel out, the graph has a hole. And when the equation is in standard form, the y-intercept is the point 0, c, where c is the quotient of the constant terms. So that is all of a review of what we covered last week, Monday and Tuesday, and then the week before that. Any questions moving forward? All right. Let's go ahead and start to look at some of the new stuff then. So the existence of horizontal asymptotes. We have seen graphs that have horizontal asymptotes. Study the following equations and graphs, answer the questions that follow each pair, and ultimately make 3 inferences about the existence of horizontal asymptotes for rational functions. So again, we're going to have multiple sets of graphs and functions here, but for right now, just focus on these two. Go ahead, look at the graphs of them, look at the functions, see if you can see any connection between them. Pay attention to where your horizontal asymptotes are. Look at your functions, see if you see any similarities about them and how you might be able to determine where that's at. So I'll give you a minute to look at that, and then we'll discuss it. Does anybody notice any characteristics about these functions? What was that? The first two that we're looking at. We're going to get to the next pairs, but we're just looking at the top 2 first. Okay, that's really important there. So, Marie noticed that the degree in the numerator is less than the degree in the denominator. So we're going to say degree of numerator is less than degree of denominator. So that's what we needed to notice. We're going to refer to this, so we could call this, in other words, so I'm going to put it in parentheses, bottom heavy. The bottom has a higher value, so it's bottom heavy. Okay, so if the degree of the numerator is less than the degree of the denominator, just like Marie told us, bottom heavy, what do we notice about the horizontal asymptote? Where is it? Marie? Yeah, at y equals 0. That's where the horizontal asymptote will be, if it is bottom heavy. Okay, on the next pair, if we look at the bottom, we have 2 more graphs. Take a look at their graphs, take a look at the rational functions. What do you notice? What connections do you see with those ones? Okay, we see that it is top heavy. So degree of numerator is greater than the degree of denominator. In other words, top heavy. What do we notice about the asymptote? Do we have a horizontal asymptote? Not exactly. It doesn't go straight across. This one would be known as a slant asymptote. So no horizontal, but there is a slant asymptote. No horizontal, but there is a slant asymptote. And we can see on both of those they go right there. Now, we're not going to do it with this example, but we are going to get into examples either later today or tomorrow where we're going to actually be able to find that slant asymptote and determine where that's at. What does that asymptote look like? Or what form do you think that would be of when we're going to try to find that? Yeah, slope-intercept form. It's a line, so we're eventually going to figure out how we can find exactly where that line is. And we'll get into more examples with that a little bit later. Any questions before we flip? Or next page? All right. All right, so now we have another group of two graphs here. What do we notice about these horizontal asymptotes, these rational functions, the graphs together? What do we notice about these ones? Go ahead, Rebecca. Okay, the degree is the same. So we're going to say degree of numerator is equal to the degree of the denominator. So this one we could call equally heavy. Same on the top and the bottom. So then to answer the question here, they provide the h of x again here for you because they want to know what the horizontal asymptote is. How do we actually find out from the rational function where the horizontal asymptote is if they are the same power, they're equally heavy? Rebecca?
You divide the numerator by the denominator.
What of the numerator and what of the denominator?
Oh, the first term of the numerator.
The leading coefficient, yes. So we would take the 2 and the 1 that's technically in front of that x. So we have 2 over 1. So y is just equal to 2. That would be your horizontal asymptote. And if you go ahead and look up at your graph at y equals 2, we see the horizontal asymptote right there. Then if we look over at h of x, we have negative 2 over 2. So that simplifies to y equals negative 1. If you look up at your graph at negative 1, we have a horizontal asymptote. Okay. What is the value of y equals a over b, where a is the leading coefficient of the denominator of h of x? Or sorry, a is the leading coefficient of the numerator of h of x, and b is the leading coefficient of the denominator. Well, that's what we had already discussed up above. We showed that it was 2 over 1, and that 2 over 1 is equal to 2. So we kind of showed this step up above and talked about that the leading coefficient is how you actually get that a over b equal to your horizontal asymptote. So we really did both steps in this one. And over here it was negative 2 over 2. So this is really showing your steps. That way if you look back at your notes when you're studying, you understand how we got that, listing out the coefficients. That's how we found these values. Alright, so at the beginning it said we would go through these examples and we would be able to make three inferences that we would be able to write about horizontal asymptotes. So at the bottom is where we're going to write these three statements. So at the bottom, The first one. So based on all that you have seen, make a list of 3 rules that govern the existence and determination of the horizontal asymptote of a rational function. So the first one, if a rational function is bottom heavy, then y equals 0, which is known as the x-axis, is a horizontal asymptote. So that was that one example we talked about being bottom heavy. We knew the horizontal asymptote had to be at y equals 0. Then we also figured out if a rational function is top heavy, then there is no horizontal asymptote because there is a slant asymptote. And then the last thing we discussed, if the rational function is equally heavy, then there is a horizontal asymptote at y equals the ratio of the leading coefficients. So that was the last example we had just seen. So these are 3 rules that we're going to be able to use while looking at these rational functions and then trying to actually graph them. You'll be able to determine where the horizontal asymptote is. So as you finish up, we're going to go ahead and try some examples now. Give it another few seconds, let everybody finish copying. Alright, it looks like everybody's finished up. Madeline, you good? You sure? Alright. Let's go ahead and flip the page then. So we're going to talk about these slant asymptotes and some examples of them. So you already noticed the connection of them. We noticed that they are a line. But we're going to try to figure out how we're going to find that line. So notice that the graph below has a slant asymptote. This will always occur when the degree of the numerator is exactly, so that's important. It's not that it's just one or more than 1 greater. It's exactly 1 greater than the degree of the denominator. So with it being top heavy, it doesn't mean that it could be x to the 5th over x to the 1st. It has to be exactly 1 greater than the degree of the numerator. Notice that the slant asymptotes are oblique lines. Oblique lines are defined to be lines that are not vertical or horizontal. They have a slope and a y-intercept. So I think it was maybe Marie that mentioned earlier, it's going to be of the form slope-intercept form, y equals mx plus b. In this case, they wrote it as y equals ax plus b. So from the graph, what is the equation of the slant asymptote? Your equation should be in the form y equals ax plus b. So from looking at the graph, determine what this would be. So you need to find your y-intercept and your slope. So by looking at that, what is my slope? That's what we're going to plug in for A. The slope of the line. Think rise over run.
It'll just be,
It's just 1, so I can just write x. I don't have to write the 1, okay? Plus the y-intercept, which is 4. So that is what the line of the slant asymptote is. And again, we were able to find that because they already gave it to us. But now we're going to try to determine how would we find that if they did not give it to us. The equation of the graphed function to the right is this function g of x right here. So this is what is graphed over there. Synthetically divide the numerator by the denominator. What do you notice? Do we remember synthetic division? So on the top, you take your coefficients. We have 1, 3, and 2. And we're going to divide that by the factor on the bottom. So what value do we actually put in this box on the left? Yeah, 1. It's x minus 1, so we actually put the plus 1 here. And then we synthetically divide. Remember, you bring the first term down, and you can go through your process. We don't need the remainder in this case. We're looking for the x value and our constant value. Remember, this was to the squared, and this value here, when we divide it, will give us 1 less power. Well, if you reduce the power by 1 from a square, you get a line. So the coefficient of 1 on the x just becomes x, and this is the constant, which is 4, is what we get up above. So y equals x plus 4 is the equation of the slant asymptote. So these are the values we're worried about. This is the x, and that's our constant. Alright, so the second one is very, very similar. We're going to go through the same process. There's going to be one thing that looks a little different though. So again, we can see the line here. So let's go ahead and look at the graph and determine what our function should be. We should have y equals what? What is this line? Emily, you have it?
1/2 x minus 1.
1/2 x minus 1. Now it says we need to synthetically divide with this here. How can I rewrite this bottom first? The top, yeah, I can take the coefficients. It'd be 1, -1, 1. I want to find out what I'm going to put in this box here. What can I do with this bottom part? What can I pull out of here? Just looking at the bottom, what can I pull out? Madeline? The 2. So I can pull out the 2 and have x plus 1. Then, if I solve for that one, the 2 would go away. Solve for x, I'd get -1 is what I'm plugging in here. Again, synthetic divide, so bring down your first term. Okay. These are the terms we're worried about, the x term and the constant term. Now, if we would just go ahead and write that, we would get y equals x minus 2. Is that what we had up above? No. So something is different about this one. We can't just write our answer. But what did we notice was different whenever we were trying to originally solve the problem? What did we do first? Madeline helped us with it. What did we do? Tori? We pulled out the 2. So with our answer down here, we didn't consider that 2 in our answer. So after you find your answer, we had the 2 up here, but down here we need to divide by the 2. So both terms would be divided by 2. Up there we were multiplying by 2. Down here we're dividing. So when you divide that, that gives you 1/2 with the x. Negative 2 divided by 2, that gives you the -1. You get the same answer as we did up above. Sorry about that. Right here. We get the same answer as we did up above. So here we had to pull out the 2. 2 was multiplied by everything, but down here we had to divide by 2. Before you turn the page, we're going to write a few steps at the bottom. So finish up that problem, and then we're going to write a couple steps at the bottom of this page before we turn. Alright, these directions we're going to write are to find the equation of a slant asymptote. Find the equation of the slant asymptote. Step 1. What do you think step 1 is? We just performed it. We did 2 examples. Go ahead. Okay, we do need to find slope-intercept form, but specifically we're not going to state that as a step. I mean, that's what we're going to arrive at as our answer. What's the first step we do in going towards that answer? Think you have it, Rebecca?
Synthetically divide the 0 from the denominator by the numerator values.
Yeah, we're going to synthetically divide the numerator by denominator is how we're going to state it. Synthetically divide the numerator by denominator. That's step 1. So we did that twice. Synthetically divided it. Step 2. Well, if you think about the second one, we had 2 steps. In the first one, we necessarily didn't have a first step, but we could have done the same step, but what value would have been used in the problem up above if we would have done the same second step? What value would we've had to have divided by up here in the second step? In the bottom, we divided by 2. If we had done the same step up here, what would we have divided by? Why did we divide by 2 on the bottom? Where did that come from? We took our answer and divided by 2. Did that 2 just magically appear? Where did it come from? Anybody? Rebecca?
You factored out the 2 from the denominator equation, but you can factor a 1 out of the one from the top.
Exactly. We don't necessarily show it because it really doesn't change our answer, but a 1 could be factored out of here. And then we could divide our answers by 1, but dividing by 1 just gives us the same answer we get. So you can go through the step, but you're going to get the same answer. So step 2 is divide the quotient by the leading coefficient of the denominator. So the quotient is the answer to the synthetic division because we were dividing. That's our quotient. So we divide the quotient by the leading coefficient of the denominator. Divide the quotient by the leading coefficient of denominator. And I guess looking ahead, I didn't realize we had a box there. I had it written in a different spot. So if you either want to rewrite it, or if you just want to write a note, on the next page there's a box. You can say you wrote it on the previous page. Sorry about that, I didn't realize the box was there. But you can either, if you want to rewrite it, or 2, just write that you wrote it on the previous page. All right, so we reviewed some, and we covered the new asymptotes and how to find them. Since we started this class a little bit quicker, since we didn't have announcements this morning, this is where I'm going to stop for today. That way the other classes don't get too far behind. So we'll stop here. You have some time though. If over break you didn't have your stuff or didn't get caught up on homework, now's a good time to maybe think back, since we went over some of that stuff. Maybe get caught up on some of that homework if you didn't have it with you at home. Or go ahead and maybe start a few of these problems, since we've got the main ideas. But you have some time that you can get started on that.